Here are the answers for the Section 7-5 Word Problems assignment. Question 1. Find the time t in seconds for a swing of a pendulum whose length L is 12 feet. And then we're given the formula from physics class about the swing of a pendulum. So let's replace L with the number 12. Our equation becomes t equals 2 pi times the square root of 12 over 32. Now, if we were physics class, probably be okay with the teacher just to type this in a calculator and get a decimal approximation for this. But our book says to simplify and leave it as a radical. So let's follow the rules from the other day. Inside the square root symbol, the fraction 12 over 32 is reducible. 12 and 32 both divide by 4. So we can write 2 pi times the square root of 3 over 8. Now let's separate that fraction into separate numerators and denominators. So we have 2 pi times the square root of 3 over the square root of 8. Now rationalize the denominator by multiplying top and bottom by the square root of 8. Now we have 2 pi times the square root of 24, because 3 times 8 is 24 under a radical, all over 8. Let's factor 24 by rewriting it as a pair of square roots, where one of the factors is a perfect square. Let's go with 4 and 6. Then we have 2 pi times 2 times the square root of 6 all over 8. What I've done there was replaced the square root of 4 with its value 2. Next up, I'm going to reduce. In the top we have 2 times 2, which is really 4, and in the bottom 8, so 4 over 8 reduces to a half. So we have pi times the square root of 6 all over 2. So here is simplified form if you leave a pi symbol in the problem. If you replace pi with the fraction 22 over 7, then you would get the same answer but in another form. Number 3, the altitude h of a cone with this volume is 6 inches. Find the radius r. So here we have the geometric formula for volume of a cone. Let's replace the capital V with 201 1/7. And replace the letter h with 6 inches. Now solve this for r. 1/3 times 6 is the same thing as 2. So let's divide both sides by 2. We get 100.85. And that's equal to pi r squared. Now divide by pi. The textbook says to use the fraction 22/7 for pi. And the result is 32.08 with a few more digits. Now to solve for r, let's take the square root. So we get r equals the square root of 32.08. And that result is approximately 5.66. The radius r is going to be measured in inches. Number 5, the maximum height h in feet obtained by an object fired with an initial velocity of v feet per second is given by this formula. Find the velocity, remember that's v, required to shoot a projectile to an altitude of 5,000 feet. Altitude was h. So let's take this equation and substitute 5,000 for h. And solve this for v. So multiply both sides by 64. This makes 320,000 is equal to v squared. Now take the square root. And v equals 565.6, some more digits, feet per second. Number 7, find the circumference of a circle whose area is 128 square centimeters. To do this question, we need to know the formula from geometry class for circumference of a circle. Pi times the diameter Or another version of this is circumference equals 2 times the radius times pi. What we're given to work with is the area of the circle, so we're also going to need the area formula. Area equals pi r squared. Let's substitute 128 in place of area. And solve this for r, so that we know what to substitute here for r. Divide both sides by pi. We get 128 divided by pi is equal to r squared. Now take the square root. And the answer is approximately 6.38 if you round. Now we know a value of r, so we can go back to our circumference formula and substitute that value in for r. Remember, it really has more digits that are still in my calculator's memory. And the result is 40.1 if you round it. Circumference will be measured in centimeters. For the review assignment, we're asked to simplify the radicals by following the 4 requirements in the section. First, let's combine these together underneath one radical. 35 times 3 divided by 5 makes 21, because 5 goes into 35 7 times, and 7 times 3 is 21. The square root of 21 would make a decimal. So the next thing we look for is, can we factor 21 into two numbers where one of them is a perfect square? And you can't, because all I can think of is 7 times 3. And neither 7 nor 3 are perfect squares. So here's our final result. Number 9. Like the last one, let's multiply these together and get a single radical symbol. 60 times 3 is 1,800. Now check to see if the square root of 1,800 will make an integer. It's easiest to do that on the calculator. Nope, when I type the square root of 1,800 on my calculator, I get a decimal. So the next thing is to try to factor that into two radicals, where one of them is a perfect square. I know that 1,800 is equal to 900 times 2. And I'm choosing 900 because that's 30 times 30. Next up, we get 6 times 30 times the square root of 2. What I've done is I've replaced the square root of 900 with the number 30. Final step, 6 times 30 is 180, square root of 2. Number 16, we want the fourth root of this fraction. Let's separate this into separate numerators and denominators. Then rationalize the denominator. The fourth root of 8 does not make an integer, but the fourth root of 16 would. So let's multiply top and bottom by the fourth root of 2. The reason I'm choosing that is so that my denominator turns out to be the fourth root of 16, which will make a nice result. In the top we have the fourth root of 162. Next up, let's leave the top for now. We can do more work on that in a bit. And in the bottom, replace it with 2. Okay, let's check on the calculator to see if the fourth root of 162 makes an integer. You can use the fourth root button if you can find it, or you can use the fact that a fourth root is the same as a 1/4 exponent and type 162 to the 1/4 power just to see what it makes. That makes a decimal. So the next thing I'm going to try to do is to factor this into two things, where one of them is a number that I can take the fourth root of. How about 81 times 2? Because the fourth root of 81 is 3. In fact, looking earlier, I see that I had that at one point in time. It makes me wonder if I should have noticed that then and simply said the fourth root of 81 was 3. So this makes 3, fourth root of 2, all over 2. Number 18, we have 20 times the fifth root of this in here. Let's rewrite it where we're separating the numerator and denominator. The fifth root of -1 is -1, and -1 times 20 is -20. At this point, it might be worth checking if the fifth root of 625 makes an integer. I'm going to type 625 to the 1/5 power on my calculator just to see what happens. Nope, it makes a decimal. So let's rationalize this denominator by multiplying top and bottom by the fifth root of 5. This makes negative 20 times the fifth root of 5 all over the fifth root of 625 times 5, which is 3,125. The fifth root of this number just makes a 5, which we then can reduce into the negative 20. So final answer is negative 4, fifth root of 5. You might be wondering how I knew to times by this. Well, it helped that I knew that 625 was 5 to the 4th power. And so with only one more 5, I would create a number that I could take the fifth root of. Number 20, let's simplify this square root. The square root of 242 makes a decimal. So let's try the factoring technique where we split it up into pieces. 121 times 2 is still 242, and 121 is 11 squared. I'm also going to factor my y cubed as y squared times a y. The square root of 121y squared is 11y, and then leave the other thing in its radical notation. Number 22. The cube root of negative 54 does not produce an integer, so let's do the factoring technique. Negative 54 can be rewritten as negative 27 times 2. Well, how do I know to do that? Because I know that negative 27 is a perfect cube. I know that it's negative 3 to the 3rd power. So having knowledge of perfect squares, perfect cubes, also 4th power and 5th power terms is very helpful here. If you don't have that knowledge, it makes it really difficult to know what numbers to look for that will work out. Let's also factor the x and the y's as x cubed times an x and as y cubed times a y. So final answer is negative 3xy times the cube root of 2xy. Number 24. Let's use the factoring technique to split it up into pieces. When we look at the x to the 7th, notice the power does not match the index. So let's split that up as x to the 5th power times x squared. For the y to the 10th, the power is a multiple of the index. So let's leave the y to the 10th in that first piece. This makes xy squared times the fifth root of x squared. Number 26. Let's separate the fraction into a numerator and denominator piece. The cube root of 1 makes 1. Now let's rationalize that denominator by multiplying top and bottom by the same thing. We know it involves cube roots. Now what do we need inside here? Well, when we look at x to the 4th power, that power is not a multiple of that index. But what is the first exponent you can think of that would be a multiple of the index of 3? How about x to the 6th power? So if we want the denominator to be x to the 6th power, what do we need to times by? We need to times by the cube root of x squared. Now we have cube root of x squared in top, and in the bottom, the cube root of x to the 6th power. This makes x squared in the bottom. The way that I got x squared was by asking myself, what thing cubed makes x to the 6th? And that would be x squared times x squared times x squared. Number 45 has all kinds of stuff going on. First, let's put everything under one radical. Now let's do some reducing in there. 2 over 28 reduces to 1 over 64. When you divide the a's, use the rule about subtracting exponents. -1 subtract -5 makes a to the positive 4. At this point, it might be interesting to know if 64 has a perfect fourth root. I'm going to type 64 to the 1/4 power on my calculator to find out. Nope, it's a decimal. So next up, let's separate top and bottom. And at this point, it's worth noticing that the fourth root of a to the fourth is just a. Let's rationalize that denominator. We know we need to times by a fourth root of something. What number can we change 64 into so that you can take the fourth root of it and get an integer? Well, would timesing just by 2 be enough? 64 times 2 is 128. Did 128 have a perfect fourth root? Let's use the calculator to find out. 128 to the 1/4 power. Nope, that's still a decimal. What if we times 64 by 4? That makes 256. Is 256 something that you can take the fourth root of and get an integer? When we do that on the calculator, that turns out to be 4. So that would work really well. Let's multiply by a 4 here and a 4 here. So now we have a times the fourth root of 4 over the fourth root of 256. But remember, the fourth root of 256 was just the number 4. So we have a fourth root of 4 all over 4. Number 53, we're asked to rationalize the numerator. Well, first let's do some reducing inside there. 6 divided by 3 is 2, and this x plus 1 knocks out one of those, leaving 4 of them left. Rationalizing the numerator means removing the radical from the numerator. You can't take the cube root of 2 and get a nice result. And this exponent here doesn't match the index either, so that won't work out nicely. Let's multiply top and bottom by the same thing that will make our numerator turn out really nice. So it's going to involve the cube root of something. Now, what multiple of 2 can you take the cube root of and get a whole number result? That would be 8, because 8 is 2 to the 3rd power. So what do you have to times 2 by to make it turn into an 8? You would need a 4. Okay, now let's look at this piece. Again, this power did not match that index, nor is it a multiple of the index. So what's the first exponent that you could use that is a multiple of 3? Well, that would be a 6. So we need to multiply by x plus 1 to the 2nd power, because 4 of them and 2 more of them would be 6 of them. Okay, this turns out to be the cube root of 8 x plus 1 to the 6th power. And we now have introduced a denominator into our problem that we didn't have before. The cube root of 8 makes 2, and the cube root of x plus 1 to the 6th is x plus 1 squared, all over our denominator. That process is called rationalizing the numerator, because it creates a numerator that is not irrational. There's no radical symbol left in the numerator.